maybe
Great.
take some time. Yes?
Yeah, it's there.
Okay.
So please go ahead. Screen's yours.
So we already had 2 talks about commercial microwave links right now, and that actually makes my life a lot easier today because I can also show you some synergies of commercial microwave links and polarimetric weather radars. And this concerns work that I have done with my colleagues Christian Qualler, Max Graf, and my PhD supervisor Harald Kutzmann. And my talk will be in 2 parts. So first I'm showing some recent developments of the CML QPE in Germany, and then I'm briefly showing some preliminary results on synergies of commercial microwave links and polarimetric weather radars, which concerns work that we also do in the RealPep research group. So, as we already have seen, commercial microwave links are part of the cellular network. And what we are doing is exploiting this specific attenuation and the linear relationship to the path average drain rate. Specific attenuation will be A in my talk today. So we have this AR power law, and we're monitoring the transmitted minus received signal level. And we already saw a lot of these DSD variational plots today. So we do rain rate estimation along the link path. And in Germany, our data set covers around 4,000 CMLs. It's almost countrywide. And before you are wondering, in the northeastern part of Germany, there is not less CMLs. It's just that we are covering with this data set a specific type of antenna, and that is not built there as much, but coverage is still there. So microwave links are about 300 meters to 35 kilometers. I think the average is about 7 kilometers. Frequency 10 to 40 gigahertz. So what concerns microwave links, it's a bit in the lower frequency range. Temporal resolution is 1 minute instantaneous measurements, and the power resolution is 0.3 to 1 dB. We get our data via Python script that runs within the network of the cell phone provider. That's normally how you get the data. So something has to run inside the network at the cell phone provider. And then while this data is pulled every minute, we instantaneously transfer it to a server at KIT. So this actually makes real-time operation possible. And we did this for a long time, actually. So we got 3 years of collected data right now. So 3 years of data in a 1 minute resolution from 4,000 microwave links in Germany. It's quite a lot. Shortly, how we compare radar and CML QPE. So we got this radar QPE on the upper left side and the CML locations. Then from this gridded radar product, we take a path average drain rate by weighted length of intersects along this CML path, and then we get what we assume to be our reference as the path averaged radar QPE, and that we always compare to our CML QPE, and it's what you see on the lower left side. We actually did quite a large evaluation, and what you see here is microwave links versus gauge-adjusted radar product. It's an hourly resolution, so CMLs are aggregated to 1 hour, and you can see a seasonal comparison. So you see from left to right, autumn, winter, spring, and then summer. I will start with the summer, where we can see actually a quite nice so it compares quite nicely. And then in the other seasons, we get some overestimation by the microwave links. So we've seen this good agreement in the warm season with quite a lot of data that we put in there, so it's quite a large evaluation. But we also see this large CML overestimation possible in the cold season, which actually makes it a bit hard there. So we have to have a lot of caution when cold temperatures are there. But actually, luckily, cold condition is quite predictable. So we are now using the CML QP mostly when it's warm. Okay, so now I'm trying to show you a short video. Did this work that I changed to the video? Probably yes.
Yeah, I can see it.
Yeah, so I will run it 2 times and then I will explain some things shortly. On the left side, you see the gauge-adjusted radar product. On the right side, you see the microwave links. And now, when we look at this time step, we see a quite good agreement. So although there is more local structure in the gauge-adjusted radar product, we see quite a good global structure from the CML product. So on a large scale, it agrees very well. Then, but if I go back to the starting point, we see that while the radar is seeing no rain at all, we see a lot of microwave links that somehow show some rainfall that certainly shouldn't be there. And that's what we call false positives in general. And that actually concerns my work, those false positives. So CML signals are not always stable, and we can have some large fluctuations even during dry periods. And I'm illustrating this with these 3 time series, where you see the signal distribution on the right side and the time series on the left side, and it's 2 weeks of data. So the upper time series shows a quite nice signal. In blue, we have the wet condition, which is according to the radar reference. And you can actually see that the wet and dry periods are quite, you can basically separate them by a threshold for the transmitted minus received signal level. So that's a quite nice time series. But these time series can also have a daily cycle. And then already also in the distribution, we see that it's not as easy to separate just by the level of the signal. And the lower time series shows that it can actually be quite impossible to do it just by one threshold. And also, if we set the standard deviation as a criteria, if there is fluctuation that might be due to rain, this doesn't always work because we can have these large fluctuations, like we see in the lower time series on the right side. So challenging daily fluctuations and also quite noisy periods. And because when you look at it and you see no intuitive rule to separate those wet and dry periods, what I did is using a data-driven approach, more precisely a deep learning approach. I used a convolutional neural network, which I trained to detect these rain events. So I put in 3 hours of time series data and I label it according to the radar reference. And what I want from the neural network is a prediction if this last hour is dry or wet. And this is going to treat it as a black box today. So I'm not going into much details, but you can find all the details in this publication that is published at AMT. So now I'm going to show you how it improved this reference. It improved on this reference event detection method, which is an improved version of Schleiss and Berne 2010, which basically uses the standard deviation of the signal to find fluctuations and then tell if there is rain or not. So on the left-hand side, we got again this scatter density comparison between the CML and the radar. On the right-hand side, we got top right the count of hours that are either false positive, so rainfall that we didn't want to detect. True positive is a rainfall that was detected rightly. And false negatives, rainfall that we missed, that we should have seen because the radar saw rainfall and the CMLs didn't. On the lower right side, you see the rainfall amount on the logarithmic scale that these hours on the upper right side contribute to. So it's the actual rainfall amount in the bins on the upper side. And now I'm going to the deep learning method. Sorry, that was on the wrong slide. And we see that the false positives got a lot less. And we can also see that the true positives actually got more. Yeah, and this sentence down here, which should be actually on the next slide, explains that. So actually, the green false positives got reduced by 40%, and at the same time, we improved on true positives and false negatives. So that was quite some improvement, which actually gives us a lot more trust also in our CML product. Now about the synergies of CMLs and polarimetric weather radars. So we already heard a lot of talks today about specific attenuation. And what we learn now is that microwave links also measure specific attenuation. So there should be something we can get out of that. Specific attenuation for polarimetric weather radars can be used for rainfall retrieval using the RFA algorithm, and it strongly affects the reflectivity at a range R by this formula. It's in a close to linear relationship with a specific differential phase, and this is a bit fast forward. Therefore, also can be related to the two-way path integrated attenuation via this factor alpha. So an attenuation correction potential is created through polarimetry, and synergies with CML-derived one-way path integrated attenuation were already proposed by Silke Trömel, and I think also Alexander Ryzhkov and Christian Quala are there among others. But those we already heard voices of today. And now I'm again focusing on this factor alpha a bit. So we want to estimate alpha, and we want to exploit this CML attenuation along the link path. And we learned that CMLs operate at much higher frequencies than radars usually. So the one radar that we are using has a frequency C-band of 5.6 gigahertz, 5.66 to be precise. And the CML frequency is 10 to 40 gigahertz. So we need to do some kind of frequency conversion for a comparable attenuation. So option one, which would be kind of nice, is to do it exactly with a known drop size distribution. But if you knew the drop size distribution, then you would have a lot of problems that we're dealing with. So that's most of the time not an option. So we do it via the AR or relation, and or KR relation it was before. And there we introduce some 20 to 30% of relative errors. So this is the formula how we would estimate our alpha. We take the 2 times the one-way path integrated attenuation converted to the radar frequency and divide it by the delta VDP from the radar. And we can, what we need is only those CMLs which are actually parallel to a radar ray to compare one ray of a radar to one CML. So here we see a small blue dot. I hope you can see it in the resolution of the stream. I think it's a bit lower than what I actually see here. But in the middle is a blue dot, and that is the radar location, and all the lines around are the CML locations. From those available CMLs, first we just take the well-performing CMLs, and it didn't change much, so that's good. So we took this 1 year of data that we analyzed, and then the best performing we used for this, because we want to have a lot of trust in them. And then what we do in the next step is only take those CMLs that are parallel to the radar ray, and it gets a lot less, and that's always something that I'm experiencing, that if you introduce some rules that are quite logical, and then you lose a lot of data that you can't use anymore. But still, we get a lot of microwave links that are somehow parallel to one of the radar rays. So what we can see here, we have these 4 panels, and the upper left is a scatter plot which shows unique CML versus radar ray pairs. The event that we see, and we just see an instantaneous measurement, so it's not aggregated, is a convective rainfall event with hail. So we expect actually quite high attenuation. The green dots are so the radar in the polar plots is in the middle, of course, and each quadrant of the plot has a different color, so that you can somehow see where the points in the scatter plot come from. This expected alpha blue line is from the CDR slope. We already saw in Alexander Ryzhkov's talk today how that is created. And then we got this estimated alpha by the VDP versus attenuation comparison. I think that got clipped off my slide, but on the y-axis of the scatter plot is the CML 2 times one-way path integrated attenuation. And what we see here is that the estimated alpha shows a nice linear relationship, but is somehow suggesting that we use a lower alpha actually than the computed one from the CDR slope. And here we have 5 minutes later, different radar location. We got much smaller VDP values, but still we get kind of a good linear agreement, and again the suggestion that the alpha should be a bit lower. Of course, there are large sources of uncertainty that we try to explore, and they mostly come from the fact that the radar height above ground is up to 3 kilometers, even more in some very small areas. And so just due to the fall speed of the drops, there should be a temporal mismatch. And if we have a 5-minute resolution from radar and CMLs, then we should actually be able to see that temporal mismatch. Due to the wind, there should be some sort of spatial mismatch if there is wind. And then due to evaporation, but also effects like drop size sorting or drops actually growing while they are falling, there can be a DSD mismatch. So for all my future applications where I try to merge CML and radar products, or where I try to fill gaps in when radar is very strongly attenuated behind a rail core, I'm trying to focus on this spatiotemporal mismatch. And our chance is that we have, with these microwave links, a network that is quite dense and spatially integrated near ground. Okay, already at my conclusions. We do Germany-wide CML observations. We have a potential for real-time operation. The new processing techniques increase our confidence in the CML QPE, and the potential synergies between CMLs and polarimetric weather radars are also quite obvious. And the downside is that this spatiotemporal mismatch is a challenge whenever you have to compare things instantaneously. Normally you would like to integrate in time or in space, and then problems get less. But if you like specific attenuation or differential phase, you can only compare instantaneously, and then it's not as easy anymore. Okay, so that's actually the end of my talk. And you can also, I will upload this, my slides later, and you can ask me anything via email or on Twitter. I've got links here, and I also, so the neural network that we are using is an open source model that you can get on GitHub. Thank you. Are there questions?
Thanks, Julius, for perfectly concluding the session by coming back to radar QPE from the beginning and to dual pole radars. And yeah, so my question will also be if there are any questions. I see that Clemens wants to ask something, so I'll unmute Clemens. Clemens, here you go.
Yeah, very nice. Especially this, there's a lot of links you showed which are parallel to the radar. So there's a lot of data really to improve then, or try to improve on the radar retrieval with adjusted alphas. Question is, did you already try to use the new alphas for, or did you try it for improving?
No, it's actually the next step that we have to do now.
Okay, yeah.
But it's also, so my feeling is that it wouldn't hurt to have a bit more data, because
not money.
Because as we've seen today, the alpha can also change, which is something that we want to investigate, how the azimuth and the alpha is, and then you need to compare obviously to a rain gauge, and that rain gauge has to be exactly in that place where you try to validate the QPE. So will be a challenge, but I think once we do more events, then we can actually get a good picture. And now we got some promising comparisons.
Yeah, but from the data you showed, we will have a lot of things to compare. I'm pretty sure.
Sorry, didn't quite hear that somehow.
But from the plot you showed, I saw that you have a lot of links which coincide with the radar beam. And for sure, you will also find a lot of pages on which you can get information.
Yes.
I think there's a very good databases to explore this more.
Okay, any further questions?
I have a quick basic question. You, right at the beginning, I think you mentioned the variety of link paths. And because I also have in the background, well, in case these link paths are really, really short, so I think you mentioned the shortest is something like 30 meters or no,
300.
300 at least, yeah. So which is very hard to compare then with differential phase shift, right? So, and I do not know exactly what the distribution is, whether that is the majority of links or whatever. But my basic question is mainly, so what is the reason for this variety? Is it just due to orographic aspects, or?
I guess so.
Okay, because sometimes just from the map, it's, yeah, okay, I cannot see the details in that map, but sometimes it also seems that pretty long and short links are also close together, but yeah, for sure, we cannot see the details here, but yeah. Okay.
Okay, so I saw that Remco has a question.
Yeah, thank you very much, Christian. Thanks very much for the presentation. Really nice work. I was wondering, at some point you showed that indeed you had issues with variations in the received signal level that basically prompted you to filter some of the links, and you showed indeed here on the middle panel a situation where I believe indeed you have basically a daily cycle, right, in your received signal level.
Yeah, and
of
that's
course that,
quite often actually.
Points to temperature, of insulation effects. You have any idea of physical causes of this? Basically, we encountered the same in the Netherlands, studying individual links in detail. Notably, we had an experimental setup here on campus in Wageningen, and similar situation.
So I guess so. Basically, yeah, so from my side, you can only get guesses. From Christian's side, you can maybe get a bit more. But so two things are possible in my mind. So one thing is like radiation or temperature that actually changes the hardware of the antenna, or that affects the hardware. The other thing is, and I'm not quite sure, you can't really see it on that temporal resolutions. You also get fluctuations at specific times early morning. And then I could think that it could also be due on the antenna that affects the antenna on a specific time of day, which are two quite different things. But that should be somehow also daytime dependent. I didn't investigate this.
Yeah, I mean, so quick comment from my side. So we have not done any detailed investigation, but in the very beginning, when we started with the first data, we did comparison with one MET station from our institute, and we saw that direct solar radiation had the best correlation. So somehow it's a temperature effect, and I guess that it's really the sun warming up the devices. But it's speculation. But at least I have one time series with correlations that prove that. But we would have to do this for all the 4,000 CMLs and then get a better picture of this effect. But it's certainly very interesting to study.
So what is your guess, Remco? Or do you have more than a guess?
I was just opportunistically, I'm a great opportunist apparently becoming these days. I was opportunistically thinking those links that have these periodic received signal levels, so which you have difficulties using for rainfall estimation, you can then probably use as thermometers. Just kidding. Now we had similar issues in the Netherlands, and actually our guess was basically that it was indeed heating up at the receiver end of the system. But the verdict is still out, so to speak. We haven't unambiguously solved this issue. So that's why I was wondering if you had any ideas. Thank you. Maybe the Czech colleagues have some suggestions. They might have run into the same issue.
Yeah, actually at E-bands, it's water vapor. but we don't know how is it at K-band. It's much less sensitive, so some of it can be also water vapor by very long links, but probably also dew and other things.
Thank you. Let's investigate this further in the future, guys. Thank you.
Just to add,